Good day, everyone. Live from Cloud City, Seattle. This is This Just In. I'm Justin, and this is the show really as part of our Microsoft Reactors, where we talk about technology that is practical and we build with it. So just a reminder that this show is part of our Microsoft and Microsoft Reactor Code of Conduct. There is going to be audience participation. And so we have a great guest speaker today, Kitty Young, who is a physicist, and we're going to be talking about quantum computing. So log into your favorite chat platform, whatever it might be, and get ready for some questions. So let's go ahead and meet Kitty. So hi, Kitty. How are you?
Hi, everyone. Hi, Justin.
Hello. Thank you for being our guest at the end of season 1 here at This Just In. There is going to be a season 2, and we missed one last week due to me needing to be out. That mixed reality session is going to be in season 2, but you are our last guest for season 1, and what a better topic to talk about than quantum computing.
Thank you for having me. This is an honor.
Yeah, absolutely. So tell us a little bit more about yourself professionally and what you do here at Microsoft.
Sure. Hi, I'm Kitty Young. I'm a quantum architect in our quantum computing team. I am a physicist, so I've been doing fundamental physics, condensed matter experiments. Now I work for Microsoft in our quantum computing effort. Using my physics background, but I don't go to the labs anymore. So it's more about helping our team build and design the whole stack of quantum machine from the software all the way down to the hardware.
Very, very cool. And one of the things that I think really inspires me about the work you do is not only what you do at Microsoft, but what you're doing with your art by physicist Kitty, some of the Kickstarter things that you've been focused on. So tell us a little bit more about what you do outside of Microsoft in the tech space as well.
Sure. I have a lot of hobbies. As you can see, maybe you look at my website, I do art, I do fashion design, and I also do music. So Art by Physicist Kitty Young is my personal account, my website, where you can see all kinds of interesting projects beyond my day job. And you mentioned the Kickstarter. That is a project that I did for my fashion brand. The brand is called Art by Physicists, which I design using my own paintings, and then I embed technologies into clothes. So you can wear clothes with electronics and charge your phone or display different images. So a lot of interesting explorations there. So I did my PhD in applied physics, which is designing computer chips, and I first started working in the semiconductor industry. So I learned a lot about scaling and designing components for hardware, and then I started exploring adding those electronics into clothes. So I don't do that for my day job now, but that's been a hobby that I've been doing on the side.
Yeah, that makes a lot of sense if you think about your professional background and your formal training, but also applying your inspiration and your visual talents. I can tell you honestly, I am not a very good visual artist. If I claim any fame whatsoever to anything creative, it probably is in music. But I really admire a person who's able to take something, inspiration in technology, and really apply it to the visual arts, whether it be fashion, whether it be the imagery that you build, something like that. The comic strips, we're going to talk a little bit about your quantum computing comics and things like that. But let me ask, what inspires you as a creator?
Well, because I'm a scientist, most of my inspirations come from nature. And there are also a lot of great artists that I really admire, like Van Gogh, and some modern artists. I follow someone called WLOP. It's kind of a mixture of classical style with anime style. So I get a lot of inspiration from how our nature behaves. When I was a little kid, I always loved gazing into the stars, and then I decided to be a physicist when I grew up. So even when I was very, very little, I wanted to be a physicist. So I kind of moved from wanting to be an astronomer to a particle physicist, and then ended up being a condensed matter physicist. But there's all of these connected phenomena in nature, and that's what inspired me both in terms of science as well as art. So when I do my art, you see my designs are focused on creating nature themed and astronomy themed paintings and fashion design. So that all come together into different art forms that I produce.
Yeah, I think what's really interesting about that too is that, quantum and quantum mechanics and quantum computing itself is inspired by nature. You likewise have been inspired by nature in the work that you do. And so there's just a really cool balance, something that just kind of works out in all of that. Well, I'm very excited to have you here on the show. Kitty, you're covering a topic that, for me, the math around quantum can be challenging for many. It can be challenging for me. I did take some maths back when, but certainly haven't exercised that particular muscle in the physics realm lately. And so help us in the audience kind of lead into some of the math around quantum. So let's begin with some of the building blocks here. And like I say, we're going to connect this with your visual art because Kitty has this incredible comic book on how to explain that. So I'm going to try to flip through some slides and give some visuals here as you explain it. But let's just begin with, help us understand the qubit and superposition, because those are super important building blocks to get started here in quantum.
Yeah, totally. And the good news is the maths involved is not very complicated. So for quantum computing, even though it is a subject mimicking nature and building computing based on quantum mechanics, we just need a few fundamental understanding of a few concepts. Here we listed superposition, interference, and entanglement. And then you need a little bit of math, which is linear algebra. That is not so complicated to start with. You can very quickly start writing algorithms based on these foundational areas. And Microsoft has this language called QSharp, where you can very easily start expressing your algorithm with this language encoding. And then you can run your algorithm all the way onto actual quantum hardware that's hosted on the cloud. So I'm very excited to be showing you this experience today. So let's start with superposition, as you mentioned. Forget about how this is quantum mechanics and is something so different from what we experience every day. Actually, quantum mechanics is experienced every day, but just forget about all the mental burden of how difficult quantum may be to understand. Let's start with something just maybe like common sense. This is for you to compare what is a quantum bit versus a classical bit. So classical bit, we know that's binary, is either 0 or 1. So you can think about any representation that may be captured with 0 or 1. For example, there's a circle, it could be empty, and you can call it a 0 because it's just a measure of information. So you can just say, okay, if this circle is 0, it is, if this circle is empty, it is a 0, and if it is filled, it is 1. And this is a binary case. Say if you have a bowl of lottery balls, and if all of them are red, you can call it a 0. If all of them are blue, you can call it a 1. Similarly, if you have a coin, there are two sides. You can call the head to be 0 or the tail to be 1. So this is however you want to label some binary system with classical bits. Whereas in quantum case, it's not just these two possible states anymore. You could have a combination of them. Say, similarly with this circle, you could have 1/3 of it being empty and 2/3 of it be 1. And in this case, you can say we have 1/3 of 0 and 2/3 of 1.
Mm-hmm.
And then the lottery is maybe 8 red balls. So 8 out of 20 is 0, and 12 out of 20 is 1. And the spinning coin it has 50% of chance of landing to 0 and 50% of chance of landing to 1. And you can see now in the quantum bit, you're essentially describing probabilities. So it's got certain probabilities of having you have 0 or 1. So if we go to the next page, we can see that the representation of a quantum bit is literally a linear combination of these two possibilities. So if you have 0 or 1, you can have a certain probability of having a 0 and certain probability of having a 1. Both of them can be represented together with a qubit. And in our graphic examples, we can have these probabilities labeled, and these are amplitude squared in terms of a superposition. So this is one equation that shows you what the state of your qubit is. You can see is A times 0 plus B times 1, meaning in this system, you could have either 0 or 1, and you could have A squared of probability of 0 and B squared probability of 1. Why squared? Because these A and B are amplitudes, which we'll get into later. These are amplitudes, and in physics, amplitude squared is probability. So in common sense, you know that if 0 and 1 are the only possible outcomes in your system, you know their probability together will equal to 1. This is kind of common sense that you can't have is if you have a complete system, you can't go beyond 1.
Mm-hmm.
That's your probability. So that's basically what a qubit is. And you may hear this, my description a little bit different from maybe popular media, because usually is a wrong description. So this here, superposition, is a superposition of 0 and 1, and your system could have possible outcomes when you measure it to be either 0 or 1.
Yeah, I think this is just fascinating. I think your visuals really helped me understand it, that ultimately the computational weight here is this probability.
Yes.
And so that allows for a huge more range of calculation potentials. I had to go all the way back to my like CS 50 or CS 101 and just kind of really get my head around binary, remember it, because we developers and software engineers, we have so many abstractions that's built on top of the binary. Think of all the libraries. That's where I spend my life now, is in new libraries and managed solutions and platform as a service in the cloud. And so I had to go all the way back to the basics and say, okay, that's what makes quantum different, because you're calculating a much more larger range of possibilities, right?
Yeah, and the same kind of abstraction is happening for quantum as well. So we don't expect quantum developers to think about how you're going to manipulate the qubit in the hardware. You just write the code on the highest level where you want to write the algorithm. So you don't have to worry like what type of voltage you're going to apply to your qubit. So just as when you write code now in classical computing, you don't think about what voltage you're going to apply to your transistor. So we gotta have a similar level of abstraction. And in my demo, I'm also going to show you how we are going to express quantum algorithm. And you would be, of course, at this stage, we are learning quantum. So we're gonna see how it affects each qubit. But then for complex problems, we are going to write just high level code without worrying about the detailed qubits.
Yeah, very cool. I think the other one of the breakthroughs that I took when I was first learning a little bit more about quantum is, you talk about systems, and that, there's a lot of talk about qubits and how many qubits and inherently stable qubits. And there's lots of discussion, and that's all encouraged, because that's how humanity advances, is that we have these discussions. But Can you tell us a little bit more about, in my opinion, the second big building block, which is the system itself? How do we build combinations of qubits?
Yeah, so I think we should go through maybe the interference and entanglement, and then talk a little bit about the hardware aspects, how you can represent those things on hardware.
Sure, I'll queue up that slide. We'll talk a little
Yeah.
bit. Is this a good one for entanglement?
This one is for interference. So let's go back to the previous one.
Okay.
I wanted to show people, because we only showed what happens with one qubit. Now with multiple qubits, you have more probabilities. You have more possible states that you can represent in your quantum system. So you can think about this like how we would represent classical probabilities with a pie chart. In the first case is what we just saw. If we only have one qubit, there are only two possible combinations of possible states, 0 and 1. But if you have two qubits, now there are 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1.
Mm-hmm.
There's no more, right?
Yeah.
If you want to express all of the possible states with two qubits, that's the 4. And each of them has amplitude in front of them, indicating how much of a 0, 0 is in your system and how much of a 0, 1 is in your system. So A, B, C, D, the amplitudes are like weights. But now if you have 3 qubits, similarly, you then have 8 possible states. So you see that the number of possible states or possible configurations in the superposition can grow exponentially.
Wow, yeah.
With n qubits, you could have 2 to the n possible configurations. But it doesn't mean that you have all these different states like parallel computers. That's a myth. That has been a misconception in popular media, is that if we have 3 qubits, we will have 8 computers running at the same time. No, that's not how it works. So I think the misconception is that this is just a representation of possible states with a qubit. The real power comes in when you can then interfere these possibilities and entangle them. So that's what we will see now. So with all these amplitudes indicating how much of something is in our system, is actually not hard to imagine something like interference could happen. So forget about quantums. Where do you see interference? You see them in waves. And what kind of waves? Like water waves, sound waves, any type of wave you experience in every day, it has interference when you have, because it's got peaks and troughs. And if 2 waves meet and they have matching amplitude, they're in phase, then their amplitude will grow. If they are out of phase, they can cancel each other. So these are called the constructive and destructive interference. So this actually happens in quantum systems because of the existence of these amplitudes indicating how much probability of something is in your system. So the consequence of that could be very interesting. So if you look at a classical probability theory on the left here, say you want to predict the weather the day after tomorrow. And there are, for simplicity, 2 possible outcomes, sunny or rainy. And if the first day is split into 50-50, maybe I'm just writing down numbers. That could be any number, but you see that in classical case, you represent it with probability. You say maybe the next day will split into 30% sunny and 70% rainy if tomorrow is 50% sunny. And then equally on the other branch, you will have maybe 2 other numbers. So this is what we actually learned when we were kids, when we first started learning probability. And we learned that In order to know if 2 days after is sunny, we just add up all the probabilities. We time the branches down and then we add them up. So in the classical case, we get 60%. But in the quantum case, because we're dealing with amplitude, we don't directly write down the probability anymore. And there's nothing preventing me from writing down a negative number.
Mm-hmm.
So the probabilities are still the same because amplitude squared, actually the modular squared will be probability, and it's always a positive number. But if you do a square root, you could equally likely get a negative number. And in fact, it could also be complex numbers, but we will not go too deep in there. But what does this negative number do? It actually does a destructive interference for your whole system. So if your system is quantum, there's nothing preventing you having a negative number that could even subtract your probability of getting a sunny day with multiple paths. In the classical world, you would think the more paths that leads to something, the more probable that is. Yeah. But in quantum, that's not actually the case. You could have more paths leading somewhere, but actually lower probability.
Yeah, I'll admit this is something that I really kind of gets my brain going, teasing a little bit on trying to make sense of the differences in probabilities. But perhaps maybe my aha moment here as a person who is learning this is that the laws of quantum are constant, just like classical. So you're still going to get this 8% in your example. Every time given the set of inputs. It's the law of numbers or the law of physics. So as long as the system of math is clear and constant, then we can predict or we can build systems around that or computationally calculate more complex things. But it's a weird one where we have to kind of unlearn a little bit what we've grown up with in order to relearn something that is perhaps even more powerful. And furthermore, there are certain things where classical, you're going to get into this, I think, a little later in the show, but there's certain things where classical makes more sense to do. And there's certain things where quantum makes more sense to do. So now we're talking about both systems and learning both at the same time, right?
Yeah, exactly. And this quantum is more fundamental than classical because classical is actually an abstraction from quantum. Mm-hmm. So quantum is more fundamental. If we look at things in the quantum mechanical way, we see, this is how nature actually behaves. And we're only seeing the surface phenomena of it in our classical world. So this interference is very, very important in our algorithms. And most of the popular content out there do not cover it. Because it's kind of counterintuitive, it's harder to understand. But that's used everywhere.
Yeah. And indeed, I think that'll be one of the key problems that physicists and other engineers working in quantum are solving is making this more approachable for everyone, whether that be through libraries where the math is built in, even like your comic book, just making it more approachable. My experience, I think 3 years ago when I first started looking at quantum is I started to sift through some academic papers, and I'll be honest, they're a little hard to get through sometimes, or I lack the context with which to be able to really separate the real meaning, the real interesting, and the practical elements of it. And so fortunately, that's the job for people like us, is to make the technology more practical and usable for most people, right?
That's right. And that's also what part of my job as an architect is kind of a translator, trying to understand the math and physics paper, but then take out the essential part to then teach people beyond who write the paper.
Yeah, absolutely. Well, I'm checking time here. I think we'll try to come back to entanglement late. We have some other questions and some great things to get through. But if you're curious about the third part, which is entanglement, Kitty and others have built an incredible Microsoft Learn module, the foundations of quantum computing, which you can really study these different concepts and get through it pretty easily. I really enjoyed reading that module myself as well. But
shall we show
Yeah.
people a screen of that? I have it open here.
Yeah, go ahead. Yeah.
Yeah, so this is the website that I highly recommend everyone look at. This is our quantum learning resource website, is azure.com/quantum/learn. And here you will be able to find all of our learning materials. And what I highlighted just now was also included in our MS Learn modules. This is what Justin was mentioning. We have a systematic course that teaches you from the concept to writing code to then running everything on Azure Quantum. So I highly recommend people check out this website as well as the learning courses.
Yep, absolutely. It's a good one. Well, let's talk a little bit more about these abstractions as we start to build more resources. I kind of, as I was studying this, I kind of jokingly thought, like, well, chances are a quantum computer is not going to sit on every desk in every home. Indeed, it's a little bit more complex than that. So, can you tell us a little bit more about what Microsoft is doing with quantum computers and how those will be used by software professionals and other people in the future?
Yeah, quantum computers are not something that you can carry with you, and at least not in the short term. So they are right now being developed in labs, and a lot of there are different types of architecture, but there's a common type that require low temperature. So what Microsoft built is using the topological qubits, where you have to cool things down to near 0 Kelvin, so very, very low, like 100 millikelvin temperature, so that you can have the quantum effect showing up in your materials. And we are hosting these in the labs, and you can imagine in the future you will be accessing them through the cloud. So you will not have like a huge fridge in your room and trying to use it to do computation, but you would rather access it through common cloud. Right now, we also already have a cloud service called Azure Quantum. This is where you can already access existing hardware developed by our partners like IonQ, Rigetti, QCI, Honeywell, now is a Quantinuum. So these are different types of quantum architecture from the topological ones, but they are ready and we have qubits available. So people can already use Azure Quantum and access these hardware to run your programs.
Yeah, and indeed, Kitty, as you were telling me as we were prepping for this too, there's going to be just a range of things that we solve with classical computing and quantum computing. And so maybe share a little bit more about the crossover point and what use cases are we going to ultimately use quantum computers for versus classical computers as well.
Yeah, so there is going to be a constant competition between classical and quantum for the problems that they can solve. But we know theoretically that there are classical computing problems that scales exponentially with the complexity of the problem. And at some point, quantum computer would be faster than those. So you see the crossover point. So quantum computer scales slower. So maybe right now at the beginning, it could still be longer. It takes longer and slower to run quantum computer to solve these problems. But then at some point, it's going to then take over and be faster than the classical ones. So these problems are the ones that we are interested in. And these are small data problems with super exponential or super polynomial or exponential quantum speed up. And those problems require millions of qubits. So that's why we need to develop our hardware and our software stacks and everything that goes into the system and the cryogenic control, all with that millions of qubits in mind. So you can see there are different grades of problems, but overall we need a huge number of qubits. That's why we need to pursue scalable quantum computing. rather than maybe smaller ones. That's good for learning and doing some exploration. But then to solve actual problems, we need to scale.
Yeah, and I think what's so interesting about this slide and some of the understanding of what it would take to get to 1,000,000 qubits, in fact, is that a lot of these examples, cryptoanalysis, chemistry, material science, this comes back to nature and the building blocks of nature. And that nature is so complex. And in order for us to be able to model nature, think of climate change or other things, connecting even some of it to the topics that we've been discussing at This Just In during this season. So cryptography, sustainable software engineering, all of those different things really require a tremendous amount of computing power to be viable. So I can only imagine, or maybe Kitty, share with us a little bit more, like what is the potential ahead in some of these key areas if and when we're able to get to that 1,000,000 qubit plus range?
Yeah, totally. We are looking at problems that are classically intractable on classical computers. And a lot of these problems are fundamentally quantum mechanical. So as you mentioned, just seeing some climate change, chemical, material simulations, fundamentally those are quantum mechanical reactions. And to use a classical computer to program, to try to simulate these are really, really hard. But quantum computer is intrinsically quantum and is kind of a biomimicking, is doing what nature already does. And at the quantum level, like electrons around a atom has a superposition of energy levels. And we can just use the superposition of the quantum states to represent these energy levels. So a lot of these problems then fall into generating designer materials or new types of photovoltaics. Those can all be useful in clean combustion, clean energy, clean water, or energy efficiency applications. You can think of so many types of maybe catalysis or photovoltaics materials that you could use quantum computer to simulate. Yeah, exactly. This shows a possible usage of quantum computing for carbon fixation, where if you want to take carbon out of the air, you need to apply a huge amount of pressure or temperature to gain that energy to go across that energy barrier to make that reaction happen. But what if you can find a catalyst that can allow you to break that reaction down into smaller steps at lower energy requirements? Then you can save so much of energy and computation. And to find that catalyst is something quantum computer could help solve and try to run simulations at a reasonable time.
Yeah, I think, just as humanity is confronted with some of the most difficult challenges, energy, climate change, one of the reasons why these have been challenging to overcome is the sheer amount of variables and the sheer amount of data that is required to get to that outcome. And so, at least from my perspective on it, I look at quantum as one of the amazing building blocks of the how humanity can solve these in the future. Certainly, as we discussed in past episodes, it's not just about fixation. It's also about reduction and about being humans sustainably using our resources. But these indeed can be the tools that we use through technology to really advance and innovate even more. So speaking of innovation, Kitty, you've worked a lot with the Quantum Development Kit and QSharp. So this is Microsoft and the open source community's answer to starting to build models and libraries to make it easier to build with quantum in the future. So I understand you got a demo planned for us to kind of share us how you use this kit.
Yeah, we have quite a lot of different ways to use the Quantum Development Kit. But I think the coolest one is to directly run something on hardware that is hosted on the cloud. So I have a demo open here. This is on Azure Quantum. So if you already have a Azure account, you can then add a workspace, a quantum workspace. And how do you do that is in our documentation. You can find that through our Microsoft's quantum documentation, how to create an account. And by the way, you can also just find it through this website that I told you, the learning website. Documentation is right there. So say you already have a account and then you already created a workspace. I wouldn't go through that. You can just follow the documentation or follow the prompt here. And once you have one, there's actually a very easy way to run it. There's a Jupyter Notebook embedded already on Azure Quantum. So you don't have to use a local environment or any other development environment. If you already have one and you prefer, of course you can do that, and how to do that is also in the documentation. But this is all embedded on the cloud. You can just start with maybe an example Jupyter Notebook. You can see we also support Qiskit and Cirq, which are IBM and Google's environment programming languages. We can show a demo using QSharp. So I already have this quantum random generator notebook open. So you see all these has already been programmed. So you can follow the step-by-step and learn how this works. This is to generate a random number using a qubit. I think we may want to show the theory how that works very quickly, because otherwise this code may not be very clear to people what's going on. So let's go to the slide. We have number 22. We can quickly show people how do you generate a random number generator. So we have a visual representation of a qubit because...
Looks like we might have lost Kitty's feed there. I think we are still live, so hopefully we can get Kitty back there as well. So while we're waiting for her to join back, let me go ahead and switch over to our slide here. Let's see. There we go. Thank you. So yeah, well, Kitty's joining back in as well. Let me share with you a little bit more some of the resources that we have. We talked earlier about the quantum computing foundations as well. So if you're new to quantum, I really would encourage you to check that out first. It's a great Microsoft Learn path just to get anywhere where a conceptual understanding, but then even just kind of a controlled descent into all of the details and the libraries that we have with QSharp and Quantum Development Kit as well. The other thing is Kitty shared earlier the quantum learning resources. That's azure.com/quantum/learn as well. That really has all of our resources, anywhere from discussing about the hardware and Microsoft's views on hardware to then how we're building the open source software as well. And so with that, Kitty, I think we got you back, right?
Yeah, my whole browser crashed for some reason.
That's all right. That's why I got a slide to say here's some more resources and stuff. But I could wax poetic about quantum, but I'm pretty sure you're the expert here. So
I thought you were already starting to teach me about entanglement.
Oh, I could have gone there next, definitely. Definitely be a little stretch for me, but I think I could get there after studying, learning from you for the last couple of weeks here. All right, please go ahead and continue your demo. We were just talking about generating random numbers when we lost you.
Yeah, I'm sure that the crash was not caused by the cloud. Two different systems. Yeah. So I wanted to show people the slide as well. If you're able to put up page 22.
Okay.
Very quickly, some theoretical grounding of this demo. We can represent quantum qubits using a visual called the block sphere. I mentioned it is a superposition of 0 and 1. And next slide, please. I think actually a few slides down. Yeah, I prepared a lot of different things like Schwarz algorithm, but we probably don't have time for that. But yeah, here is the essential concept. So we can consider these superposition of qubits in a multi-dimensional space. And when you only have one qubit, that's only a 3-dimensional sphere that you can just represent 0 and 1, these two states on this sphere. And there are other places on the sphere you can get to by applying gates to your qubit. And essentially what these locations on the sphere can be represented as vectors, and then gates are just matrices. So when you apply matrix to vectors, you change the vector where the vectors are. So here I'm showing a particular matrix that can move your states from either 0 or 1 to an intermediate state called plus and minus. And if you look at how what plus and minus look like, they are basically a superposition of 0 and 1, with the only difference one is 0 plus 1 and the other is 0 minus 1. So now if you put your qubit into this state and then you do a measurement, you could either get a 0 or a 1 at equal probabilities. So if you do measurements many times, you would just keep getting either a 0 or a 1. So in effect, it is a random number generator.
That's interesting. Yeah.
In this case, we know that the probabilities are equal. So you get equal probabilities of 0 and 1. But in other cases, you could have different weights. Then when you do the measurement, you could have more of one case than the other.
And you can express this all through QSharp by basically processing with the library that is as if it's a qubit, but you generate this probability of 1 and 0 as a result of it, almost like it was like classical computing.
Almost, yes. But in this case, you are putting your qubit into a superposition.
Yeah, very
and you're actually measuring on actual hardware the probabilities of these outcomes. So we can now go back to the demo. This is probably the simplest demo for quantum. We can do it in a very short amount of time. And this doesn't involve entanglement yet. If you want to learn about entanglement, actually all these things could take hours to teach. I gave a class on Hackaday, and that's also linked through the links that we are sharing here. So this basically tells you that there are some libraries that you can open. You can define the measurements and the gates you applied. And here, there's some operation. This is basically QSharp, how you can write, represent a qubit and gates using QSharp. So you basically define, you have some qubits, and it could be any number you can set. And then you apply to each qubit a H gate. So that's what we talk about. H comes from a name called Hadamard, the person who came up with the matrix. So apply to each basically allows you to bring all of your qubits into superposition, and then you can do a measurement. For each, you do a measurement. Don't be bogged down by the type of measurement yet. There are actually different types of measurement. This is the Z measurement. It tells you along what axis on the block sphere you want to do the measurement. But don't worry about it for now. But this is a very simple code, very simple generation of random number using a qubit. So you basically just run these on the cloud, and here is running on a simulator. We have simulators enabled on classical computers. You can predict what could happen to a quantum system. So that helps us with development. So if the number of qubits is 3, you can run this multiple times. And you can see this time is 0, 1, 1. You can run it again, you get a different outcome. So you can just keep running that, and it would show you different outcomes. So that's random.
Can you run 1,000,000 qubits on it, or would that take a little bit of processing time?
I haven't tried that on the simulator, but for the classical, for the actual hardware, you can't do that yet because the available qubits in this case is 11 on RNQ. So it could take you some time to realize that you can't do that.
We're not going to try that on a live demo, are we?
Yeah, but like on the simulator, you can put in. I haven't tried a huge number. This is up to you. Maybe later on when you try the demo, you can put like many and see what comes out. Yeah. Okay, so that's just the theoretical part on the simulator. Now you can then connect to Azure. This is my subscription. It's automatic. So you can just run the cell and then you get connected. And it shows you that you have access to RNQ, QPU, and their simulator as well. So you can then run the same code. You don't have to rewrite any code. Just run the same thing on Azure, on RNQ QPU, or you can run it on the simulator first to test your code. Up to you. So this is a good development step. If you are writing a very complex algorithm, you probably don't want to use your actual hardware resource before you prove that it works. So you can run it on the simulator first, and then if it's okay, you can then change it to the QPU. This is where you would set the numbers. I actually ran one before, so this is a history from before. So to run this on I don't know why the simulator is taking a while, but to run on the hardware, it usually takes some time to do. So I did this some time ago and saved the result for you to look at because we don't have time to wait. So in a different notebook, I basically did the job in the actual hardware. And I should be able to then show you what comes out. So in this here, you can use the Azure status, put in your job number to see I had one succeeded. And then you can do Azure output to see the outcome. So in the actual hardware, there's noise. So you will see a little bit of difference in the probability, the frequency of the outcome that comes out. But if you did this on a simulator, it would not have the noise, so you will have a perfect outcome. So let's see, I just ran this on a simulator. So then I can remove this. By default, it should show the last result. I guess, yeah, it asked me for ID for that. It's okay. We don't have time for that, but I can basically.
I mean, this certainly gives us a good illustrative understanding. I love how you can use Jupyter right in, basically, you're right in the Azure portal, writing in a Jupyter notebook. And and Kitty, also, I think what's interesting about this too is maybe share with us, like, what's the difference between QSharp and maybe more general purpose programming languages like Python and C#? Like, how orient us to what is the part of the QSharp and what is more general purpose here? Yeah, so you saw here the earlier command has a specific gates and libraries that is quantum specific. Yes. But then the whole thing can be embedded into classical languages. So QSharp is interoperable with Python or C#, other types of languages. So it's all
together. So when you are running quantum programs, you actually need to use some classical computation. So the
Yeah.
language itself is also interoperable. You just need to write whatever for your quantum part in QSharp, but the rest of it could be classical. And this brings up an interesting point also about quantum intermediate representation, where in classical computing, you need intermediate representations for different type of hardware and different type of languages. Similarly, we have different languages for quantum. Like I mentioned, we have Cirq and Qiskit and other quantum languages. And there are also different types of hardware. So we don't want to have a basically not a simple way to gather all the quantum language input. And then we have to, if we don't have intermediate representation, we need to go to each machine needs to have a set of libraries for different languages. Similarly, for different languages, you need to have separate libraries for different machines. So that's a total mess.
Yeah.
But we have a quantum intermediate representation that takes all kinds of languages in and then translate it for all kinds of hardware.
And that's so important if the community wants to innovate. And I think it's one of the reasons, in my opinion, why I see the open source community contributing to QSharp and other things, Microsoft being part of that and working across the community as well, is it's gonna take a lot of effort to bring these things together. And to perhaps my background is a little bit more in web and web development in a time long ago. And when we talked about standards and web standards and how we can all be interoperable together in that, and this has parallels, except we're just getting started in it as well.
The nice thing about it is all of these are open source.
Yeah.
The language, the intermediate representation, and there's a lot of collaboration between different companies and organizations and universities. So everyone can contribute. Everyone can work on this open source stacks to be able to build your own solutions. And we also need a lot of people to be in quantum. We need people from all kinds of backgrounds, software, hardware, or not maybe communication, not even hardcore science engineering, but we need all kinds of skill sets to come together and help develop this industry.
Well, that's a great bridge to people. We've got just a couple minutes left. One of the last questions I had for you is just kind of thinking about the skills market and the skills opportunities for quantum. And so if you are a student or you are a professional that's looking to switch careers or try something new, how do you get started in quantum? What do you recommend?
There are many different entry points. And conventionally, people may say you need a PhD in physics or math, like you need to understand all of the theoretical part of it. That is much needed, and especially for hardware development and the system, the cryogenic control systems and algorithms, you need these theoretical background. And usually students can learn in school to go into these directions. But for people who are already in a different area in industry, they also have entry points, especially through software. You can find all these resources that are open source and all these courses that are available online. You can just get started, learn a language, learn how you write algorithm using any of the existing languages, and start contributing on GitHub, on maybe write your blogs, your experience learning quantum. And there are so many ways that you can start learning and get into this industry. And especially I would recommend this self-learning for anyone who's already working. Quantum is new for everyone. So even though I have a PhD in physics, I had to learn it. I didn't know anything about the software, and I didn't know anything about the fundamental theory. even though I did hardware and condensed matter physics and studied quantum materials. I had to learn all these things. And then I entered quantum through self-learning and teaching other people. So you can do similar things, and we have all these resources available for you.
And what I love about this, quantum and the quantum innovation that is coming is that if you are a student of math and you're trying to decide what area of physics I want to go into, if indeed that is your career path, this is a highly applied area. There's a lot of elements of theoretical physics. I have some good friends that I grew up with in my college that were theoretical physicists, and we'd have these debates around the practical and the theoretical because, in my career, I took a very practical approach in that. But if you are a physicist or a mathematics person or someone and you aspire to move to a practical space, that's what's great about this is that there is real innovation here on the hardware and on the physics side. But then there's equally as much innovation in the software side and expressing quantum as, in forms of what is approachable or interoperable with classical computing. So much work to be done. It's a great space to join, I think, certainly right now as well. Well, otherwise, Kitty, do you have any other advice for people who are interested more in quantum or, anything that they can do to prepare for a quantum revolution tomorrow?
I would highly recommend people to just get hands-on with it.
Mm-hmm.
Don't worry about the theoretical math. Start using some of the existing tools offered by Microsoft and go through our learning materials and maybe read some textbooks. I think that would get you, whether or not you end up joining quantum as a career, I think this is a super intellectual area that's interesting. And this is human trying to learn from nature and build a machine that could help us understand nature better. Mm-hmm. And that's intellectually engaging. Yeah. So I think this, no matter what you think quantum as an industry, how they will evolve, I think this is an area that humanity is entering into, and quantum mechanics and through quantum computing can help you understand our world much better.
Yeah, as I said before, it's an amazing how. It's how we may be able to solve humanity's toughest challenges in the future. So, Kitty, thanks again for being on our episode here of This Just In. Very, very interesting. I learned a lot in the process of working with you on this, not only on the software side, but I think I finally started to get my head a little bit more around the math and the hardware and where we're headed in that as well. So again, thank you for your time. Really wish you luck on your Kickstarter and Art by Physicist Kitty too. Really inspiring work there. And,
we actually have already done that. Yeah. It was a successful Kickstarter.
It was. Congrats on that as well. So thank you very much again for all of you out there who are watching our episode here. Do feel free to get some great resources if you want to learn a little bit more about quantum. Check out Kitty's website there, and season 2 of This Just In is coming. So thank you again, and have a good rest of the day. Cheers.
Thank you.